Hello and welcome. To those of you coming to see Plenary 3, we're going to wait one more minute for our on-time departure. Okay, I'm going to go ahead and get started. Welcome to the Plenary 3, the data-driven analyses and visualizations in response to COVID-19. I'm Eric Lind. I'm Manager of Research and Analytics at Metro Transit, which is the biggest public transit provider in Minneapolis, St. Paul, Minnesota. And I'm really excited about this session. We have a number of really good talks about how people have been responding to, obviously, the global issue of pandemic of COVID-19, and specifically how it's impacted transit. Before I get started, just want to do a few reminders. First of all, this session is being recorded, just so that's clear for everyone who's presenting and asking questions today. Because it's a plenary, we are going to use the Q&A function in the Zoom to record and then answer questions. We have a series of lightning talks, so we're going to wait until the end to do kind of a more discussion-based Q&A. But as questions arise, please feel free to put them in the Q&A interface inside Zoom. If you have technical difficulties, you can use the chat, and Willem is here to help us navigate those issues as they arise. And then finally, to presenters, as we've talked about, we'll be giving them 6 minutes to get their presentations done. At 5 minutes, I will interrupt them with an audible ding and let them know that they have a minute left. So with that, I'm gonna get started. So before turning it over to our great presenters, I just wanted to give a little bit of an overview perspective on what's been going on with COVID and transit. And I think hopefully what you're seeing right now is something that looks familiar. As I look around the web, I see a lot of slides and data sets that look very much like this, which is that mid-March came along and the world changed. So this is something we're all dealing with, and I think some of the presenters are going to talk about not only how are we dealing with this, but how did we even measure what was going on? How did we change from a monthly NTD reporting framework to a daily, oh my gosh, what's happening framework? And the technology and the process behind that is something that's very much a transit data problem. So this is one lens that we're looking through of just a real change in how many people are on board. Strangely, at the same time, we have another issue, which is that just as we've lost a lot of riders, we're also not able to carry as many. So this is in Minneapolis, St. Paul, a map of departures where we consider the bus to be kind of COVID overloaded. They're carrying more than we'd really want to see on board from a safety perspective. So whether it's due to loss of drivers, due to health-related reasons, or because we're just at 50% or below capacity on our vehicles, we have this new challenge with COVID. Like, there's not many people riding, but we don't have enough room for them. So I know we're going to hear about these two dynamics that are going on, and it'll be cool to see what different solutions that agencies and partners have come up with. The third challenge is something that is sort of highlighted by what happened in Minneapolis in May, but is not something unique to Minneapolis by any means. This is a picture of a bus stop taken May 29th, so just a few days after George Floyd was killed here in Minneapolis. It's a Route 5 bus stop. It's one of our busiest, or it's our busiest bus route. And what I like about this picture is the emphasis that transit is embedded in communities that are experiencing all kinds of challenges during COVID-19 and other challenges that are not started with COVID-19 and certainly haven't ended with it. So as we're doing a lot of introspection as an agency about how we serve communities that have experienced trauma, we need to sort of bear in mind that we serve a very specific role, and we have a lot of work to do to make sure that we're doing it well. So with all those three thoughts said, I think I'll let us get to our presenters. Before we do that, because there is a particular focus in thinking about the number of people that are using transit on board simultaneously, and there's some cool new technologies we're going to hear about for sharing that information. I wanted to start with three quick poll questions. So Wilma, I don't know if you can share those. So this is a 3-question poll. The first couple are supposed to be for transit staff only, but feel free to answer if you happen to know in your particular transit service area. And then the third one. So first, how much information do you have about passenger load information? Second, how do you tell your customers about this? And third, what is a reasonable expectation for riders? Or what do you think riders really want to know when it comes to vehicle overloads? So I'll give everyone just 30 seconds to go through that. And then maybe we'll come back to, we'll let people vote kind of through time. We'll come back to that after a talk or two, if that's okay.
Yeah, I can leave it up for a few minutes while you go through a talk or two, and then,
okay.
And then we can look at the results.
All right, sounds good. All right, so without further ado then, I'll get started with the talks. And to lead us off from the CTA in Chicago is Raymond Chan. So take it away, Ray.
Thanks very much, Eric. Hi, my name is Raymond Chan. I am the business intelligence developer at the Chicago Transit Authority in the data analytics team within our technology group. And today's presentation is going to be on the COVID Customer Tools Historical Bus Crowding Dashboard. And so some of the goals of our dashboard that we had laid out in late May was to provide all customers with a tool that allowed them to be comfortable with taking transit. And that meant to utilize the current data sources that we had to describe the vehicle state, the load, where it was on the network. And we really couldn't be collecting additional data at this point. So whatever data we had in-house was the data we were going to use. We had to develop and deploy a web application, a custom web application, and update the application with new data as new data came in every week. And these were really critical, as you'll see in a second, that we did it ourselves rather than going out to bid or to ask an outside vendor. Some of the challenges that we saw in doing this was data presentation. So a lot of us here use data every day. We're not scared of a ton of data, especially those who use big data tools and R or Python or other data visualization technologies. But to the average consumer, we didn't want to build something that was overwhelming. And we tend to do that, I would say, in both a planning and data community of just kind of slamming lots of data out. But that doesn't really work for the public. So we really wanted to build visualizations that were inviting, but not overwhelming. We also want to design for all users, not just desktop users while we're developing, but also mobile users for those out and ADA users for those who don't necessarily have the same abilities as everyone else. Next, time to market. We couldn't wait 6 months to a year for an outside vendor or a technology consulting company to come and develop an application for us. We really had to get this application as soon as possible for obvious reasons. And we had to do it in a way which it was customizable if guidance from CDC or another public health agency provided different information, different guidance for us. And lastly, cybersecurity. We couldn't sacrifice cybersecurity while we were deploying these applications. We really needed to minimize and or reduce the risk exposure for us from a cybersecurity perspective. So some of the things that helped us in the beginning when we were going with this is that we already had a bunch of stuff laid out and was available for us. So we had a semi-centralized data storage. It's not perfect, but it's, I would argue, one of the most complete data warehouses or data lakes in the transit industry. We have a long history of data preservation, organization, and usage. From 2003 on, we've had a bunch of data minders that have helped us keep and maintain data over a long period of time. And we're constantly adapting to new technologies to enhance data usage, from the cloud to Hive and Hadoop, to really increase query speeds and to unlock more data for our analysts to use. And we have a lot of experience with continuous integration and continuous deployment of applications. We develop a lot of applications in-house, and we're able to really provide a lot of tools with a small staff. So some of the technical specifications, this is something that you can just take a screenshot of and send it to your application development folks or those who are trying to do this as a customized web application. It's hosted in AWS. We built it with JavaScript and Vue, which is a JavaScript framework, and the visualizations are done with Vega. That's a visualization framework, comes out of the University of Washington. And API and data files are exposed away from our internal system, so they're hosted completely in the cloud. So from our data standpoint, we take the bus data off our vehicles, we clean the data with our APC quality control tool, we migrate our data warehouse, we do a weekly extract and insert into our application automatically. So there's no one every week kind of doing the data mining and data preparation. So some of the features that we're able to bring out from this is our mobile-friendly infrastructure. So our application works completely on mobile and on desktop. On the right-hand side, you'll see our mobile-friendly interface with the shortened route names and trying to maximize as much real estate as possible. With the complete control over the application, we are able to really design for different types of folks. Some of the things that we learned along the way was that screen reader technologies are really heterogeneous in the industry. There's a lot of different ones for a lot of different folks. iOS does it differently than Windows, and really being able to design for all users was a really big challenge for us. And extensibility, our flexibility to add custom user interfaces, such as route sorting. You know, our routes don't sort alphabetically, as well as adding additional modules was really important to us. So we really wanted to be able to take this application, use it as our framework to allow us to add additional features like our forthcoming historic rail loading data and our real-time information data that we're trying to deploy as well.
Ding.
Thanks, Eric. And so this is sort of the desktop user interface. It works the same way at the URL below. So if you want to see how we're doing with crowding, you're welcome to come look at it. It's color-coded, and it also has tooltips, and it's also colorblind friendly, and it works really well with a lot of screen readers. It allows us to select routes and schedule types, as well as see sort of an overall crowding pattern along a variety of routes. And with that, I will give the rest of my time back.
Excellent. Thank you, Ray. That's very cool stuff. Summarize it as your data were ready, your app developers were ready, you were ready, even though you didn't know it. Okay, so next we're gonna turn it over to Logan Nash from the MBTA in Boston. Before I do that, I just wanna emphasize what some questions have been asked in the chat about those poll questions. First, just answer them the best you can. If you don't work at a transit agency, you can do other and indicate that. The answers will be shared probably after the third presentation. So you still have time to vote. With that, Logan, take it away, please.
Thank you, Eric. So I'm Logan Nash. I'm from the Customer Technology Department at the MBTA, the transit agency here in Boston. I'm going to be talking about how we communicated real-time crowding information out to riders. I think this is a great complement to Ray's presentation because CTA was first out there with historic crowding information. We focused on real-time information first, although we're both working on sort of getting both kinds of information out to riders. So, and Ray's great. We've been coordinating all summer long. So, and Eric, I think your slide, I can probably skip over this one because I think your slide did a great job kind of setting the context that we're all working under when we're talking about crowding information during the pandemic. In Boston, as everywhere else, we saw that bus ridership tended to be more durable than rail ridership or express bus ridership. And in particular, we saw that transit service that was most ridership was most durable in when transit service was serving sort of our most vulnerable communities, low-income communities, communities of color. These are riders who are essential workers who do not have the flexibility to work from home or take a different mode. So these are really the folks that transit agencies sort of need to be paying attention to and serving right now more than ever, and the folks that I think everyone on this call is trying to serve while doing this work with crowding information. So we first started working on this back in April, and we had this sort of extra challenge that, well, even in the best of times, we in the customer technology department at the MBTA are not representative of our ridership. When we build technology for our riders, we like to go and talk to them about it, talk to riders who aren't us, do interviews, conversations, rider intercepts on platforms and it stops. We can't do that during the pandemic. And it's especially challenging because right now, we're not even riding the service ourselves, right? We don't know what it's like to be an essential worker who depends on transit during this crazy time. So we did something we don't normally do, which is that we did a survey, got this out via a lot of different platforms, trying to specifically reach transit riders who are continuing to ride the MBTA during the pandemic. We got a lot of responses, which is really great, from a lot of different neighborhoods across the Boston region, including places where we continue to see crowding. And I would love to sort of talk a little bit more about like what we found from the survey, because it is very interesting, some great quotes from riders. But I think I'll focus in on what I think others have already identified, which is that there's really two kinds of crowding information that we can give to riders. And those kinds of crowding information have very different uses. So there's real-time information, which we found really seem to be most useful for riders who are taking essential trips. They're already in transit. We can't sort of help them change their plans too much, but we can give them greater sort of confidence and a feeling of safety potentially while they're already taking transit. Historical trends are a little different, right? That is more useful for riders who have flexibility, maybe who are returning to riding transit after not having done it during the pandemic. I think that gets us really excited as transportation people. Like, we love the idea of sort of shifting the peak and all that stuff. But here's the thing, the people who are taking transit right now, essential trips, they don't have a lot of flexibility, right? They're working on shifts. They need to be at a certain place at a certain time. So we really focused on real-time information because it was available on our bus fleet where crowding was happening, and because that seemed to be the sort of the first, the most urgent use case sort of right at this moment. So this is a bit of a diagram about how we're getting that real-time information, that real-time crowding information from our buses. I want to be very clear that this is patched together. Like Ray said, no transit agencies had the time or the money to go and buy a lot of like fancy new equipment and install them fleet-wide to get information out to riders, right? We needed to do a good job with the tools that were sort of already at our disposal. So we are using automated passenger counters we already had on most of our buses. These were never meant for live information. They were meant for historic ridership NTD style reporting. So sort of hacking it together, part one. They're also communicating to us over our dispatch radio system. So not cellular, the radio, which has sort of the kinds of bandwidth limitations you might expect from a system like that. And then that's coming through to us in our dispatch system, our legacy CAT-AVL system, Transit Master, which, while that is a legacy system, we've also over the years gotten very, very good at just strip mining whatever data we need out of Transit Master in real time. So we have our own in-house application. It's called Busloc. It does sort of the math of taking those APC messages that are coming off of our buses through our dispatch system, calculating real-time loads, and then sending that information where it needs to go. So that goes out to our operations supervisors in a daily report, identifying where crowding is happening. It goes to our in-house mobile dispatch app, Skate, to our inspectors in the field who are managing service. And most importantly, it goes out in our public-facing API so that riders can see it on countdown signs, on MBTA.com, and of course, third-party apps. So this is what, as Ray mentioned, we have to think about how we're presenting this information to riders too. So there are GTFS real-time specs for crowding information. They didn't make a lot of sense in the pandemic, so we tested 3 different categories with riders to see what makes sense. You'll notice these are simple, these are color-coded. We wanted to make these as legible as possible so that even riders with sort of limited English proficiency would be able to take advantage of this data. And the important thing is that it's out there right now. It's on, if you go to mbta.com/crowding, you can see what routes it's available on. As everyone else here did too, we are struggling to get this data out as quickly as possible. And I think we're really proud of the fact that we were able to get this information out to riders in 3 months. That's the kind of stuff we like to be able to do with technology, even when it's under crazy circumstances. So that's my presentation. I'll say, if you're interested in the work we do, come check out mbta.com/techjobs. We are, believe it or not, hiring under these circumstances, and wanted to share sort of a number of the folks on the MBTA team who contributed to this project in a number of ways. So I've got their photos on the screen for you. Thank you.
Thank you, Logan. Very cool stuff. Okay, so to kind of complete the story when it comes to real time and looking at passenger loads, we're going to have Jasmine Eftekhari talk to us about the APC ridership tool for demand response planning. Jasmine.
Thank you. Thanks, Eric. Hi, everyone. I'm Jasmine Eftekhari. I'm a service planning analyst at Toronto Transit Commission's Research and Analytics Department. And today I'll be talking about using the APC ridership tool to develop a demand responsive service plan during the COVID-19 pandemic in Toronto. As I'm sure you all know, the COVID-19 pandemic developed very quickly. By March 17th, most employers implemented a remote work policy. By March 23rd, both the province and the city of Toronto declared a state of emergency. All non-essential businesses and schools were ordered to close. And by the beginning of April, TTC's ridership declined to about 15% of normal. But we did see some variation by mode. Our bus ridership declined to 22% of normal, and our subway ridership dropped to about 10% of normal at one point during April. This wasn't a surprise to those who understand Toronto and the TTC network. Our subway mostly transports passengers to the downtown core where the most offices are located, but the bus network, on the other hand, serves low-income neighborhoods and essential industries such as food manufacturing and distribution. About a third of our customers don't have access to a household vehicle, and similar to a lot of other transit agencies, people still relied on us to conduct their essential errands, such as grocery shopping and going to work. And the people that relied on the TTC mostly relied on buses, and they weren't taking the subway or the streetcars as often. While we communicated with the community that passengers should only be taking the TTC for essential trips, we still knew that we would have challenges in maintaining physical distancing. The capacity of a 40-foot bus that normally carries up to 50 passengers, as you can see in the graph on this slide, was reduced to 15 customers. We were concerned with instances of crowding and also the number of times that 15 customer threshold was exceeded, and we wanted to minimize crowding as much as possible throughout the system. So obviously this meant that service had to be maximized, but this had its own challenges. At the beginning of the lockdown, there were challenges in maintaining our operator workforce because of childcare issues and also the self-isolation requirements. This limited the number of operators and also vehicles that we could dispatch. As the ridership drop continued throughout April, the loss of revenue generated enormous fiscal challenges, and we had to implement service reductions. But despite the ridership decline, we still had reports from our operators and our route supervisors, as well as on social media, that we had crowded vehicles on corridors that served low-income residents and essential industry. So during the early days of the pandemic, we developed and implemented the demand responsive service plan. This meant a reduced level of scheduled service and the deployment of run as directed or RAD buses to fill in the gaps on corridors that were still experiencing crowding. And as the economy opened up, we needed to be ready to report on overall activity, crowding, as well as deploying resources to various locations if needed. So we needed to develop a tool to help us identify which corridors to send these RADs to, and also generate KPIs for crowding. We are one of the few transit agencies in North America that has APC on 100% of our bus fleet. And this gives us a huge amount of data to help produce a statistically valid daily reporting and tracking. The tool that we were going to develop needed to tell us how much, where, and when crowding was happening. The data had to be shared across the commission, especially with folks at Transit Control. Working with ITS and our APC vendor, we were able to produce a daily ridership database that could be imported into a GIS web application for visualization, and the database could be analyzed to produce KPIs, especially for crowding. In addition to the GIS web application, which I'll talk about on the next slide, the data is used to produce a daily crowding report of number of bus boardings on the entire system. Since mid-May and with the gradual resumption of certain activities across Ontario, we've been preparing for an increase in ridership and changes in our customers' travel behavior. The graph that you can see on this page on the right side shows the return of ridership as measured by bus boardings, as shown now by the blue line, and also the percentage of trips that had 15 or more customers, 15 customers on board, which is shown by the red line, also percentage of trips that had 25 customers, so 50% of the capacity of the bus on board.
Ding, ding.
Okay, thanks. In our GIS tool, which you can see a screenshot of on this page, the APC ridership data is presented in the forms of various attributes and variables, which are calculated since the beginning of March 2020. These variables include the number of trips at every bus stop across the city, ridership activity, and also stop-by passenger loads. The variables are displayed using categorized symbols, as you can see in this image, and also using heat maps, which you can see now. So this map shows crowding across our system as defined by the 15 passengers per bus. And as you can see, corridors of Jane, Wilson, Dufferin, and Eglinton are crowded corridors. And this map in particular helped our planners to develop service plans and also helped our operations to identify which corridors they had to send their RAD buses to. The APC ridership tool was developed by integrating ridership data with TTC's enterprise GIS platform. And the platform allows users to filter layers based on date and time of day and to extract the data for further analysis. As part of the demand responsive service plan, the TTC has prepared a 100% service plan while taking into account crowding levels and various drivers of transit ridership. You can see a map of the plan on this slide. The plan will restore peak service on crowded corridors and also will continue to maintain reduced service on routes that have shown very little or no crowding. So just to summarize very quickly, now I'm running out of time, the maps offered by the APC ridership tool enable the TTC to respond dynamically to demand and crowding on our buses by deploying service to known hotspots, which were experiencing crowding. It also allowed us to maintain a service guarantee of 30 minutes or better based on ridership demand and provide service on high ridership corridors and also plan for future service. Thank you.
Thank you, Jasmine. Very good. Okay, well, I have two short things. First, please keep continuing to put in questions in the Q&A box, but just for those of you that have done that already, we're going to save the answers until the end so we can keep keep focus on the presenters as we go. So, but please keep adding the questions, and if you stick around, we'll have plenty of time for discussion and answering those questions. Second thing is, Willem, I wonder if you could share the results of the polling that we have been doing.
There's a slight bias towards the last answer in the first two, because that's where I had people put if they didn't know, but I've been watching and they have not changed much. So the distribution's pretty good. Here is the results.
Great. So it looks like a majority or plurality for historical data from APC, which is good. Although a quarter of the responses said none. How many of those are actually from agencies? I don't know. Most agencies are not communicating vehicle loads to passengers, which rings true. What Ray and Logan shared is, I'd say, cutting edge stuff. The one I'm most interested in is this last one. And it looks like many people think that real-time information about the number of people on board the next trip is something that customers expect to know. And I think as we think about the transit data that's available to us inside agencies, we might have a good discussion after this about how realistic it is to get from this point where most people expect real-time information to the answers to question one, where maybe not everybody has that information even available inside the agency, how to make those two work together. So thanks for participating in that. And then let's continue with our program. So next we're going to hear from Omar Kabani from the University of Toronto. Omar.
Yeah, coming up. Hi. Okay, so hi everyone. My name is Omar. I study at the University of Toronto, and I work with Dr. Stammer Adrabi. I'm a Shelley Bed in Klubenhover, and this is our work on using data from Twitter to support planning and operations for transit systems. Our work is funded by Calgary Transit, NSER, Q-Trick, and S&P North America. To start off with some motivation, we think that the potential of using Twitter in public transit is not yet fully explored, and there are three categories here. First off, under social analysis, we know that it's good to look at what is being said, but also to see who is saying what, how do we know each other, and who are the key players in these discussions. Next up, we need to look at eyewitness tweets or in the moment tweets, which are tweets that describe something happening right now. For example, these tweets on the right-hand side. These can be disruptions or incidents. And if we can somehow identify and prioritize these tweets, we can actually help the agency pick these issues faster and respond to them faster. And the last thing is that we need to look at extracting data from text of tweets, such as location and topics. So the top tweet mentions masks, which in today's context relates to COVID-19. The bottom tweet mentions drugs, which can fall under security. And it also mentions Southland, which is one of Calgary's LRT stations. So by looking at text, we can get information about location and categories. So for methodologies, we worked in two parallel streams. For the network analysis, we start off by getting a bunch of transit tweets and then filtering them temporally, semantically, and socially. For temporal, we look at the timestamp, and then we can drill down on what you want to look at. For example, I can look at tweets sent in the month of July, during weekdays, during the AM rush hour, for example. For semantics, we developed a lexicon of terms that assigns topics to tweets based on the text. Like we saw earlier, masks indicates COVID-19. And we have 11 categories that cover COVID, staff interactions, ride quality, trip, travel time, etc. And lastly, for social filters, we can focus on tweets sent out by influential accounts only, which have high followership, or by communities that are identified using the Logan algorithm or using the InfoMap algorithm. Next, we use Twitter followership to build a social network. And then lastly, we analyze in parallel the tweets and the network. For tweets, we look at the sentiments and semantics. And for the network, we look at node count, edge count, density, average path length, and degree distribution. On the other hand, if we look at the eyewitness tweets, we can first start off by identifying eyewitness tweets based on a classifier which we developed, which uses 13 features that depend on verb tenses, sentence structure, as well as terms. For example, terms such as I just saw, or there is, or on my bus indicate an eyewitness tweet, whereas terms such as yesterday, tomorrow, and if I do not. Then we use the lexicon to extract topics. And lastly, we use sentence structure combined with leverage chain distance and non-phrase chunking to get information about the location. And this can be a vehicle ID, a bus stop, a station, a public place mention, a bus route, or an LRT route. So just to briefly cover, on the social semantic analysis, we are currently developing a tool, which is a web-based tool, to be piloted with Calgary Transit. And it conducts this analysis, and it has team functionality. It has the ability to create custom analyses and reports. And this is a sample output of what the reports page looks like. For the results of the social semantic analysis, this is just a small portion of what we can get. This is tweets that are sent out by influential accounts for Calgary Transit for the months of May and June. And as we see that with slow recovery in ridership, we have a big increase in tweets. And obviously, COVID dominates discussions. And interestingly, in the month of June, we had a peak in communication tweets because it shows the importance of communications during a pandemic. And it also is because there was an upcoming app released by the agency later on that month. So the discussions kind of fell under this category. To focus a bit on eyewitness tweets, on the left-hand side, we have the same breakdown, but only for these eyewitness tweets. And it's a bit different because it's mostly negative, because it means that when riders report something live or right now, it's mostly a complaint. And also we see it kind of spikes at security and safety, because that is something that everyday riders care about a lot. On the right-hand side, we have the breakdown of these eyewitness tweets by location. And we see that it's mostly around 3/4 of the tweets mention exact location, which shows that exact location mentions are actually a defining feature of eyewitness tweets. Lastly, we are able to geocode these tweets and plot them on a network map. This is the case for Calgary Transit. It allows us to see what is being said and where. Here we have public place mentions, as well as C-train stations and bus stops. And if you combine this with the semantic, sentiment, and temporal analysis, we can generate very valuable insights about what is being said about incident patterns.
Ding.
To conclude, we can use network analysis to provide a new dimension to gauge rider opinions. Also, if you flag eyewitness tweets, this can help the agents respond to incidents faster. And this can also be expanded to the context of COVID-19, because incidents can be something such as a sick rider using transit, and they shouldn't be. Or it can be riders not abiding by guidelines such as physical distancing or wearing masks. So this can help the agency pick these things faster and respond to them appropriately. And lastly, we see that spatial and temporal analyses reveal incident patterns. This is everything I have to present. Thank you very much.
Thank you, Omar. Thanks. So we are halfway through our session right now, doing very well. Thank you all for keeping on time. So moving from Twitter analysis to another app that I'm sure we're all familiar with, and has become something of an information provider, as well as just a trip planner in transit app. So please welcome Jonathan Sheff. Take it away.
Thank you so much. Let's see. Can you see my screen?
Yes.
Great. So I'm Jonathan Sheff. I'm a data scientist at Transit App, which I assume everyone in this audience knows. And I think in my 6 minutes, I'll just try to provide a broad overview of the kinds of analyses we've done at Transit that we think are helpful during COVID-19, but also just about mobility as a service apps in general and how I think they can be helpful. These points are some of the main ones I'll hit on. Early on in the pandemic, we looked at needs and demographics of active and lapsed users. I think there's a very much a phase one that, especially I think Eric and Logan touched on, that riders dropped, who's still there? But I think that was widely answered. But I think it touched on the usefulness of mass surveys to compare different agencies and regions. We've done real-time demand modeling using user behaviors as well as geotemporal shifts in ridership. That's been pretty useful in sort of the phase 2 kinds of questions that have been asked. Multimodal behavioral shifts, and then crowding, I think is really important right now, and I'll touch on that as well. And yeah, as I said, I think one strength of mobility as a service app data is that you have one source for many, transit app is an international app with that can allow you to compare, Boston to Philadelphia to Toronto, and that's a very useful thing that we've been able to do. So everyone has a chart like this apparently, but early on, I think the difference is that we built our demand model based on app usage, and it was nice. It correlated quite well with ridership stats where they were available. And as I said, instead of just having single ridership stats from each region that are coming out usually with a delay and measured differently, you have one metric, imperfect metric for sure, but you have one metric to compare regions. And that was useful early on to understand, where we could see that, in the South and Midwest of the United States, for example, you could see that the drop happened less dramatically and later, things like that. So another thing that I'll highlight is our survey work. I think it's been a really important and useful way to ask questions quickly of riders. We're able to send out surveys and analyze them in the time frame that's useful during COVID-19. And so, again, early on, there was sort of this phase one questioning of just who's riding. And I think that has been answered quite well across different agencies. But we found, this is in North America, we found a racial disparity as well as disparities in gender, income, and obviously, it was primarily essential workers who were still riding. That was a useful tool early on in the pandemic. Later in the pandemic, we asked other questions, especially about crowding and risk thresholds of users, and as well as when they plan on returning. I think there's some things in agencies' control, vehicle cleaning, mask requirements, but a lot of this is outside of their control. A lot of it is how safe people feel regarding COVID-19, and it's a public health question. So we were able to parse those two things. So on this slide, for example, you're seeing a response. We gave them different stages of COVID-19, where one extreme, COVID is just over due to mass vaccination, and on the other end, it is as it is now. And that was a really interesting result. We were able to understand people's needs for riding public transit outside of what public transit could do. I think a really nice result from that particular question is, if you look at the last line, less than 5% of respondents said that they would never ride again. And we're also able to parse what kinds of respondents say that. So there are people who are actively riding, who are using the app and presumably using public transportation. And then there are people who aren't using the app and not using public transportation. That the people who said they were never going to ride again were predominantly lapsed users. But it's a nice result that less than 5% said they'll never ride again. It showed, at least among the respondents, that there is still a plan to return. Regarding car usage, a lot of agencies asked us this, and we were able to ask our users in surveys. If you look at this top line, for example, of the people who said they'll never resume using public transportation as they did before, 67% of them own cars. Whereas if you look at the last line, of the people who are just riding the same as they used to, only 13% own cars and 81% don't. I think that was a really nice example of how our survey work can test some of the hypotheses that we have out there in the field. Again, these are just a few results from different things that we've done. And so if you have questions or just more in-depth questions, feel free to ask me about them later. Other work we've done is looked at geographic distributions. This is Dayton, for example, and we were looking at geographic distributions before COVID, during peak lockdown and during reopening, and trying to understand which parts of Dayton might be disproportionately active during COVID. I think this was really interesting work in part because I think in the public eye, the conversation around public transportation is changing a little bit, where because of the conversations around essential workers and equity and disparities, people are understanding that public transit in a way is a vehicle of equity and they're understanding how important it is that public transit continue in some way. And I think a lot of agencies see themselves as a vehicle of equity. And so I think these kinds of analyses where we're trying to understand who is disproportionately still riding, I think that's been really valuable. And then crowding. So Logan talked about this a lot. We actually display crowding in the transit app, and we use the standard that the MBTA developed of the 3-tier standard. So that's what you see on the middle screen. And I won't get into this. We can talk about it another time. But we're working on displaying real-time data when that's available, historical data, crowdsourced data, and predictive models. We're trying to get out as much crowding information as possible, because I think that's what people need to feel safe and make informed decisions about riding public transportation. I think it's emerged as probably the core, one of the core issues in public transportation right now. So those are a few of the things that we're doing right now. It's a longer, deeper list that we're doing, so feel free to contact me. My email's right there. If you want to see our demand model that we published, it's at transitapp.com/coronavirus. And I just want to thank you for having me.
Thanks, Jonathan. Great. So next we're going to hear from Faraz Agari, who's going to talk to us about what is happening with COVID and public transit in Iran. Faraz, you ready?
Yes, I'm ready. Can you see my screen?
Yep, we've got you.
Hello and welcome to this presentation. In this presentation, the impacts of COVID-19 pandemic on public transportation demand in Tehran have been studied. My name is Faraz Agari, and I, on behalf of Nima Aminpour and Mohammad Amir Ahmadian as co-workers, and Dr. Amir Samimi from Sharif University of Technology, and Dr. Said Saidi from University of Calgary present for you. Coronavirus spread easily by physical contact between people. So the number of infected people increased rapidly, and that leads new travel demand patterns to be appeared considering time and place. So there is an urgent need to new operational plans. And in addition, restrictions are another thing that appeared after COVID-19. So this is necessary to identify the most vulnerable zones to emphasize more strict restrictions on that areas. In this research, we use AFC data of Tehran subway and BRT from July 2019 to July 2020, and daily number of infected people in Tehran from February 2020 to July 2020. Now let's take a look at number of infected people and travel demand in unit of passenger kilometers. Passenger kilometers calculated from OD matrix, and that calculated from AFC data. As it can be seen, both curves reduced with almost same slope with 7 weeks lag, and both curves see their minimum with 7 weeks difference. So it seems the number of infected people trend follows travel demand with 7 weeks lag. This graph shows how demand changed temporally. In May 2020, the number of trips almost halved, and in April 2020, when there is a New Year holidays for Iranian people and national lockdown has been accomplished, the number of trips sharply reduced. In May 2020, a second evening peak has been appeared, and that's because of the governmental jobs reduced their working hours. And in June 2020, the restrictions reduced. Comparing July 20 to the same period in the last year, the reduction in the morning peak reduced less than the evening peak, and that's because of that new evening peak. So the morning peak is more challenging to be controlled. Spatial travel pattern changes is another aspect of new demand. In this figure, a portion of each station in July 2020 compared with July 2019. This figure illustrates that spatial pattern has not changed much, except the north of the city, because this region is more prosperous area of Tehran, and people in this area have more transportation alternatives. These two figures compared most crowded stations at each peak. In one hand, in the morning, the stations in residential areas are more crowded. And on the other hand, in evening, the stations near commercial centers located at the city center are the most crowded stations at that time. About 1/3 of travels in each peak happen in these highlighted stations. So by prioritizing these stations for more strict restrictions, the probability of virus spread reduced very much. Crowded stations at each direction has been compared in this figure, and as it can be seen, in the north and the west of the city, the reduction is more than the other part of the city. And in the downtown, the stations near educational centers experienced higher demand reduction, and that's because schools and universities were closed during during the pandemic. And based on our observations, average trip distance increased from 8.8 increased, and the number of total trips reduced. So short trips reduced more than long trips, and that means passenger hours reduced. And another thing that observed is that the busiest subway stations in the peak hours have remained the same before and during the pandemic, but during this time, BRT stations have been changed. To conclude, we observed consistent lag between weekly COVID-19 cases and weekly transit use in Tehran. Time series analysis of this correlation is one of our future works, and new operational plan is needed for the new travel pattern. And based on this analysis, crowded stations have priority for more strict enforcement and restrictions. And thank you all for paying attention.
Thank you. Thanks for sharing. I'm still trying to digest that infection and transportation lag figure. Might have to come back to that one. So next up, we have Patrick Meredith Karam, who is from MIT, who is going to talk about the relationship between ride hailing and public transit. Patrick, when you're ready.
Okay, good afternoon, everyone. So I'm Patrick Meredith Karam, and I'm a master's student with the MIT Transit. This project is about the relationship between ride hailing and public transit in Chicago, and the approach that we've taken to analyze this relationship and how we've applied that to the COVID-19 pandemic. So first, the motivation behind the study. We're seeing declining ridership on the CTA as a general trend over the last few years, and this is often attributed to transportation network companies or TNCs such as Uber and Lyft. On the other hand, there's the potential for TNCs to improve ease of access to public transit. And so this gives rise to the overall question of whether TNCs are replacing transit and when and where this might be happening. This study also benefits from a wealth of data availability, including TNC trip records and transit data. Give a high-level summary of what we're doing to predict overall. The overarching idea is to understand the nature of the Chicago TNC public transit relationship at in a location-specific and time-specific manner. And to do this, we want to adapt and develop an analytical framework that we can use to classify TNC trips according to their relationship with public transit, and finally apply this framework to both ordinary operations and to a case study of the COVID-19 pandemic. So in the bottom figure, we see overall idea of this framework. We have a set of TNC trips which are taken in real life, and we attempt to categorize each of those trips as complementary, so the trip connects to transit, independent from transit services, there's no feasible transit alternative available, or substitution for transit, meaning that transit could have feasibly completed the same trip in a comparable time. Jumping right into the results, we can see on an aggregate level results for 4 analysis dates, 2 before COVID-19 on the left and 2 after on the right. And most notably, we see a clear reduction in trip numbers. Before the pandemic, trips were sitting over 400,000 per day, but this decreased to 86,000 on March 24th and 37,000 on March 31st. And if we look at the shares of independence, complementarity, and substitution, we see that complementarity plays a fairly small role, an extremely small role in pretty much all trips. And independence takes on the dominant share around 3/4 before the pandemic and growing after the pandemic as the rate of substitution. We can also look at spatial trends in this. So we see under ordinary conditions, rates of complementarity on the left, independence in the middle, and substitution on the right by census tract. And it appears at first glance that complementarity is concentrated around rail lines, independence is concentrated in areas not necessarily served by rail transit, and substitution is concentrated in the downtown core as well as some of the rail lines. We can quantify these observations using cluster analysis to identify hotspots. And we see hotspots of complementarity around key rail stations. We see hotspots of independence outside of the rail network and concentrated on the south side of the city. And we see concentrations of substitution, again, in the downtown core and along some of the rail lines. Looking into the impacts of COVID-19 a little bit, we can see the spatial distribution of pickup locations. And before the pandemic, here on the left, we see a heavy concentration in the downtown core and to the north side of downtown. And these areas, particularly the north side, seem to lose trips disproportionately to the rest of the city as the pandemic sets in. Finally, we can also look at the temporal distribution by time of day, both before COVID and after COVID of the trips, as well as of substitution, complementarity, and independence. And before COVID, we see significant peaks in travel in the morning and evening, as we would expect, but these are also associated with spikes in rates of substitution indicated by the red line. And this would likely indicate that a lot of work-based trips could have been feasibly completed by transit. After shutdowns, we see that substitution remains fairly consistent across the course of the day, and the overall morning and evening peaks are somewhat flat. So from this, we can reach a number of conclusions. First, we've been able to expand the methods for determining the TNC public transit relation. We've identified a small role of complementarity in the overall set of trips, and as well as distinct concentrations and spatial clustering of independence and substitution. And we've also been able to look at some of the impacts of COVID-19. So first, it's been associated with a decreased role of substitution in TNC trips, particularly around downtown. And we know that many of the trips that were lost were work-based morning or evening peak trips from the north side of the city. And this identifies that this wealthier area of Chicago is disproportionately contributing to substitution trips for public transit under ordinary conditions. Thank you very much. And email here and if anyone would like to discuss further.
Thank you, Patrick. And there are people already asking you questions. So there's definitely going to be some discussion. Thank you all for continuing to attend this session. We have one more lightning talk before we get to Q&A for all the presenters. So last but certainly not least, Jiali Zhou is going to talk about how to model virus transmission risk. Take it away.
Okay, thank you. So can you all see my screen?
Yes.
Okay, so my name is Jiali Zhou. I'm a PhD student from Northeastern University, and today I'll be talking about virus transmission risk in urban rail systems, a microscopic simulation-based analysis of spatial temporal characteristics. So for the objectives of our research, we want to develop a risk assessment model for the heavy rail system. And here, the risk is a function of OD demand, infection rate of the disease, wearing mask behavior, ventilation in the trains, carrier rate, exposure time. And with this model, we can evaluate impact of mitigation strategies and operating characteristics, including mask wearing, ventilation in vehicles, and frequency and reliability of the services. So here's a flow chart for the risk assessment process. First of all, we input the OD demand into the line simulation. And this line simulation is a very detailed microscopic simulation. And the simulation will output OD flows and travel times by train. Then we input another source of data, which is the fraction of infected passengers and fraction of mask-wearing passengers in the population, to obtain the number of infected and susceptible passengers by segment and by train, so that we can estimate the overall risk. And starting from now, for the risk analysis, we use the actual data from a subway system in one of the US major cities. And this page is for the spatial patterns. What we're showing here is a heat map of expected number of secondary infections per train trip by OD pair. So the x-axis is the destination stations, y-axis is the origin stations. Each cell is representing the secondary infections per train trip per OD pair. So as you can see, there are some cells that's having relatively higher values. And these cells are actually the OD pairs that's traveling through the downtown area. And if we look at the entire system, the top tapping stations rankings goes like this: station number 8, 9, 10, and 6. But then if we look at the top risk contributing stations rankings, the rankings is different than the tapping stations. This means that the busiest stations is not necessarily the highest risk stations. The risk is also related to the exposure time, as well as the OD patterns, the trip distribution along the line. And for the base case, in our analysis, we consider 100% demand pre-COVID, and then no mask wearing, standard ventilation rate. The next page, what I'm showing here, is the impact of single factors. And here we represent the risk as a ratio to the base case risk that we just talked about. And the risk is the y-axis for these two plots. And the x-axis is the demand levels ranging from 10% to 100%. And the left-hand side is different mask wearing groups. Right-hand side is different ventilation groups. So from these two plots, we can tell that mask wearing and ventilation can help us to lower the risk. And if we focus more on the plot on the right-hand side, which is the ventilation groups, and then compare the risk difference between ventilations 80% and ventilation 100% to the risk difference between 100% to 120%, you can see that the decrease of the risk is different. Actually, the underperforming ventilation has more implications on the risk. And the next page, what I'm showing here is the risk under combined impact. These are the heat maps of the risks under combinations of different factors. The y-axis is the mask wearing proportions. X-axis is the ventilation rate. Each cell is representing the risk under 100% demand, which is on the left-hand side, and 60% demand, which is on the right-hand side. and the risk is a ratio to the base case risk. And generally speaking, the higher mask wearing and higher ventilation rate can result in lower risk. And mask wearing can compensate the underperforming ventilation rate in the vehicles. And the risk is much lower for the same combinations of factors with a lower demand, which is the 60% demand here. Let's compare the top left corner of these two plots, which is the worst case risk. So the values are 1.6 versus 0.5. And on the next page here, what I'm showing is another heat map for the combined impact. These are all 100% demand. Okay, and the left-hand side is the risk under different levels of mask wearing, which is the y-axis, and infectiousness levels of disease, which is the x-axis. Right-hand side is the risk under different levels of ventilation, which is the y-axis, and the infectiousness of disease, which is the x-axis. The boundary that we plotted is the border between 50% to 60% of the base case risk. So whatever that's below the boundary, below the border, is the scenarios where we have the risk that's lower than 50%. And we can tell that with mask wearing, risk can be lower than 50% under all infectiousness levels. But on the right-hand side, even with high ventilation, under just a few low infectiousness cases, can we have risk lower than 50%. So math is more effective. And this is the last result I'm gonna show. It shows the impact of operations and service reliability onto the risk. So what I'm showing here is a histogram of infection probability associated with individual trains under the same average headway, but with different regularity of the headways. When the headway is not regular, with the coefficients of variation, CV equals to 0.4, we have more extreme infection probability, as high as 4%, if you look at the x-axis. Yeah, and the conclusion for our research is that mask wearing and ventilation are effective in mitigating transmission risk. Mask wearing is more effective, and reliable and regular services are important because they can help us to reduce the risk. And the high-risk locations can be identified by looking at the spatial patterns, and we can use them for entry control or mask distribution as some of the key locations. And that's it for my presentation. Thank you.
Thank you, Xiaoli, and thank you to all of our presenters. Really well done. This was great. I love the lightning format because it's kind of like a little advertisement for the details. But of course, that raises a lot of questions about the details. So we have a number of questions in the Q&A box here, and people have been upvoting them with the little thumbs up there. So if people are interested in sticking around for the discussion, what I'm going to do is give you a second to upvote some questions if you want to do that, and I'll work my way from the top down, kind of trying to combine questions where I see fit. If presenters feel comfortable, please go ahead and turn your video back on, and I would encourage all the presenters to chime in if they have thoughts on a particular topic, even if it's addressed to one presenter, because this is meant to be kind of collaborative answering, hopefully. So I think that said, I'll start with a question that was directed at Patrick, which seemed to be popular, which was, could you say a little more about how you obtained and then classified the TNC trip? So if there's kind of a quick methods overview there.
Definitely. So first, addressing the question on accessing the data, this is something that Chicago, I guess, is really fortunate for. It's actually publicly available if you Google TNC trips City of Chicago. The City of Chicago has a public data portal where they put up the trip records. So that was great. And I can also post a link as an answer to that question. In terms of how we categorize the trips, we used a 3-level kind of analysis. The basic idea was first looking at service area. So how do the origin and the destination of the TNC trip relate to transit services? So that's looking at their proximity to transit stops. So first of all, is it even within the service area? Secondly, we wanted to find out if the origin or destination was very, very close to a transit stop, how likely is it that it was being used to access transit services. And for that, we used a process that we developed with some people at the CTA, where essentially we were using points of interest as a proxy for non-transit activity around the station, and seeing how likely it was that people would be accessing the station as opposed to other services nearby. And then to find out finally whether transit would give a viable alternative, we compared the service quality of a hypothetical alternative transit trip. So if you were to take transit, how long would that take in terms of travel time, as well as in terms of the number of transfers? And so would it be possible to take transit? But if anyone wants a even more detailed discussion, happy to answer that as well.
Great, thank you for that. So there's some questions for Jiali about how you measure the risk level in maybe a little bit more detail. Like, how did you combine all these different variables into a single risk model? And then, you know, that's obviously a complicated question, but maybe you can give us the shorthand. And I think there was also a question about like kind of what other research you're drawing on to make those estimates.
Okay, thank you. So thank you for the questions. So actually, our risk model is based on a widely used transmission probability model that's in the public health area, which is called the Wells-Riley model or Wells-Riley equation. So this typical Wells-Riley equation takes the ventilation, infectiousness of disease, and exposure time, and also number of infectors or the carriers into the consideration. Yeah, but the typical one hasn't considered the OD patterns, OD characteristics, and also the dynamic characteristics of public transportation. So we made some modifications for that so that we can take into the crowding levels and different demand levels, etc., into account. So that's the answer for that question, I guess. Yeah.
Thank you. So let's see. So for Omar, you know, one of the things that I was thinking about when I was looking at your analysis, which is very cool to like have a real-time type sentiment analysis of what people are saying. You know, I'm sure a lot of transit leaders would like to have that. You know, one of the things I was thinking about is, you know, back to George Floyd, thinking about the role of police in transit. You know, there are some people that want to see more police because they see things that are happening that they don't want to have to encounter, and there are some people who think that they don't want to encounter the police because that's its own different problem. So how do you, I guess I'm kind of broadening a question from Raphael Dumas about how do you take into account kind of who's reporting things and then what action you take in terms of enforcement, especially around, you know, describing other people's behaviors?
Yeah, that's actually a great question. I'll start off by the broad and then go down to the more specific question in the Q&A answer. Yes, some tweets do report what they call suspicious behavior, which can be, you know, which can be flagged under many umbrellas, which can be even just racist tweets. Twitter is not very filtered, so there's some, you can just tweet whatever you want to say. I think what our aim is to just flag what is being said and then leave it in the hand of the agency for them to take the appropriate action. So if something is deemed as quote unquote suspicious, it's maybe worth checking it out. And then if it really needs action, then go ahead. That being said, our analysis was mostly on tweets from February or like maybe April till July, which was during the pandemic area. So the portion of tweets that described incidents about security was lower because there was less ridership. But nonetheless, there were tweets that actually described something unsafe, like, you know, some angry passenger or someone that's under the influence, shouting and yelling and whatever. And there were just others that are just describing what they call shady. I just want to mention towards the end that there is research done in 2014. Maybe I'll post a link in the chat afterwards that says that majority of tweets that are about public transit are actually complaints about other people. And there's a big category that describes that just falls under racist tweets, such as, you know, against race, gender, and color. So all that stuff is basically, unfortunately, out there.
Thanks. Yeah, I'm sure we all know that it is a reality that all this stuff is out there, and it's interesting to see how it, combines or complements other channels that people use to get back to us about how our service is going. Okay, so we have a question from Brendan Hemley, which I probably should take as organizer of transit data, which is going great, by the way, Brendan. And for Raymond and Logan, and this is really a broad question that kind of those poll questions we're getting at, which is, how do customers interpret these different types of information, the historic versus the real time? Do they understand that they're looking at different sources of data when they look at historic versus real time? Kind of what are your thoughts on that? Logan, you're shaking your head, so you go first.
Yeah, I think the short answer to that is no. And I think that's reasonable. It's a lot. We're here because we're interested in transit data. So of course we want to know the fine-grained details between a live prediction and a scheduled prediction, and real-time crowding versus historic crowding. Our riders just want to get where they're going safely, right? So we actually, when we did our user testing, initially we heard from riders that hey, crowding information is great, but still the most important thing to me is the arrival prediction or the departure prediction, right? So we decided we were going to put the real-time crowding information for our buses kind of in line with our other real-time data, like arrival and departure predictions. So there's no crowding dashboard right now on MBTA.com, for example. It's just that when you go look at departures for your bus route or on MBTA.com or in Transit app, the crowding information is there with the prediction. So we actually tested out because we're looking at sharing historic crowding trends like Ray and CTA have done. And we tried out, okay, well, what if we do the same thing with historic crowding information? Like go to this routes page and we'll tell you typical crowding, and then we'll also tell you what's going on right now. And when we did a little bit of testing with some riders and found that people got really confused over that. So actually what we're doing is for the historic crowding information, partially because we think that that's really kind of a pandemic specific tool, the historic crowding trends. We don't think that's going to be that useful after the pandemic. And partly because we just wanted to steal all of Ray's good designs, we decided that for that, we actually are going to have a separate dashboard. So the real-time crowding information lives with all the other real-time information on schedule pages and stuff. The historic crowding trends, those are special. You have to kind of go hunt those down. So we hope that'll be enough of a differentiator for riders.
Yeah, and I'll chime in and say that we're also stealing all of Logan's stuff as much as we can. But it was definitely something that our senior leaders, our senior executives are very concerned about, with having customers understand that this was historic. So the name of that dashboard changed multiple times, but one of the things that we had to do was just move the word historic to the front, just to make sure that people were really clear on what it was. And it's something that still worries us to this day, but I think we've managed it since it's been a separate piece, and it was kind of a PDF report at first that kind of transformed into a dashboard. So there wasn't this expectation that this snapshot picture was going to be what's currently out there.
Great, thanks both. Yeah, and I'm sure there are many agencies that are looking to steal both of your ideas and code where possible. Don't worry. Jasmine, I wanted to turn to you because basically you're presenting the use of very similar information, but in kind of on the fly planning and dispatch. So there are a couple of questions about that in the chat. I guess I'm going to take the moderator prerogative to ask you one different one, which is how did the workforce respond to kind of this more on-demand scheduling and dispatch? Were operators happy to have go from a fixed route schedule to something more where they're just kind of on standby, or what was that like?
I wasn't dealing with operators on a day-to-day basis, but from what I know, we were previously using RAD buses. It's just that the proportion of schedule to RAD changed a little bit, and I haven't heard of any issues or any problems in terms of operators wanting to switch from schedule to RAD.
Okay, thanks.
Eric, I'll say that.
Oh yeah, go ahead, Logan.
We at the MBTA, we've similarly, we shift our reduced schedules, have a lot of run as directed operators and shifts. And I think that worked well. I think we had a similar experience to you all in Toronto, but I've heard sort of informally feedback from, you know, our operations, like our supervisors at our garages, that it's hard to manage, right? It's hard to like sort of look at a day in front of you and be like, okay, where do I think all these people are going to slot? How do I manage these resources on a day-to-day basis? It's like we're kind of asking operations staff to become kind of like, you know, low-key schedulers, right?
Yeah.
So I think there's going to be relief at the end of this month when the MBTA returns to service that is mostly scheduled, and those schedules are adjusted to, I think, reflect some of the on-the-fly adjustments that operations has been making since April.
Yeah, and that relates actually to another question for Jasmine from Jason Lee, which is about the routes that have been continued versus discontinued. And so Jason says that it looks like TTC decided to keep the local routes and discontinue the commuter express buses, but other agencies have done different things. I guess he's thinking about San Francisco eliminating a large number of other routes. And do you have any insights on the success of that approach?
Yeah, so thanks for the question. We didn't want to eliminate our local routes because mostly we're concerned about reducing accessibility, and especially for people that were transit captive or needed to get to like essential work or running essential errands. And in fact, on the other hand, one of our main goals was to actually maintain our 30-minute guarantee minimum of headway. So that was one of the main reasons that we didn't end up cutting any of the local routes, but we did cut our express routes, as I think it was mentioned in the question.
Thank you. So I'm going to skip to a question for Jonathan about the demographic data that you've collected. So I mean, I've been really impressed with everything that Transit App has been sharing, but it does come up the question sort of how do you get that demographic data? What proportion of the rider base do you think, based on that, you're really capturing, kind of what your user base looks like versus the ridership? Those are a couple of questions that people have had.
Yeah, that's a great question. We do our survey work through the app, so people have to have the app installed to answer a survey. It either appears as a banner in the app when you open that app, or we send a push notification. And that's how I was able to parse users from, lapsed users from active users. So if people open the app and they came through the banner, they were presumably opening the app because they're using public transportation. Like they don't, they don't open Transit App to play games or anything. So, and then we can make cohorts of inactive users, people who haven't opened in the app in a long time, and send them push notifications. So it's definitely a convenience sample, and it's a convenience sample of Transit App users, which is a biased sample. In the work we've done to look at representation, it obviously varies by region. Like in areas where we just launched, then we'll have a smaller adoption rate, and then I have bigger questions about representation. In some cities, we have as much as an 80% adoption rate. I'd say our typical for a medium city or something might be around, I don't know, I'd say like 10 or 15% of riders use Transit App. So it's a great question. It's going to vary by region. I've done some work looking at representation in specific regions, and yeah, it's varied. So when we work with a lot of different academic groups, including the University of Toronto, and in Toronto we've found actually pretty good representation. It will really vary. So for the person who asked the question, if you have specific regions, I can probably do a better job of answering about your specific.
Unmute. Great. Thank you. So there are a couple other questions that maybe I'll throw out to people in general about crowding at stops and crowding based on changes in frequency. How are you thinking about those in terms of modeling the disease risk? How are you thinking about those in terms of what the service has to look like to reduce, basically crowding during waiting or the resulting overloads of trains or buses? So, Jelly, do you want to answer part of that?
Yeah. Thank you. So about the crowding in the vehicles, as we mentioned, the risk model that we developed already taking into account. So according to some of the results, so suppose that we are decreasing the frequency in order to match the decrease in demand, then the risk might increase disproportionately because the service might be more not reliable, not regular, so that the run times, dwell times is gonna increase a lot. Then the exposure time increases and also the load increases. So this is gonna be a contributor to the risk with regards to transmission risk. Yeah. And for our model, I think the good thing is that we actually take each car of the train into account. So that's the answer to that question. Yeah, thank
you. Okay, anybody else? Yeah, go ahead, Ray.
So I know that there's a lot of questions over how we have a lot of data, and we definitely have the data crowding at specific stops and information that's at a lower level of granularity. The question isn't necessarily can we compute the information as so much as can we communicate in a way that doesn't end up overwhelming the user, right? I sort of took an informal sort of market research poll amongst our planning staff, and then I positioned against just, I'd say, yuppies and people who've recently graduated college who are generally intelligent. And just of a simple question of I'm gonna put it on a map, and the planning folks are all like, maps are great, we love maps. And the normal folks are just like, I don't need a map, I know where I'm going, that's just too much detail, I don't care about the satellite view, just tell me how crowded my bus is, right? It's a really interesting dynamic, and I think part of the struggle is not just communicating the data. We don't want this to be a data dump for the public, and we don't want this to be a open data portal. We want this to be a useful tool, and that's part of the problems that we're finding in the design process.
Yeah, that's a great point. Okay, so we have 3 minutes left for this discussion. I appreciate everybody who's still hanging on listening. This has been fascinating for me, so hopefully other people have enjoyed it. I want to give anyone who wants to a chance to answer Anna D's question, which essentially is, what is the new normal in transit? I don't want to touch that one, but if anyone else has a lot of thoughts, I guess the question is, based on what you're seeing now, are those graphs that we're all showing going to come back to something else, or are we entering a period where we're doing different business? So speak up if you have thoughts.
I'll go. This is Ray. The one thing that's really interesting, to dodge the question in particular, because that's what I do as a government official, is if you ask people whether or not they feel safer flying or they feel safer road tripping across the United States, and a lot of people say road trips, but road trips are immensely dangerous for a number of reasons, being that cars kill more people than almost anything else in the United States. But people have this perceived risk of being close to other people, regardless of the other risks of death out there in the world. And I think that's something, there's just the psychological barrier of taking transit is something that I think we have a long way to go in overcoming to make sure our customers feel safe. Not just are safe, but feel safe. I think that's a distinction that I want to make.
Jonathan, do you have any thoughts as someone who's working with lots of data from lots of agencies, how to put a bound on normal now?
Yeah, I mean, I think the period we're in is going to last a while. I think from our survey work, but also just our contact with a lot of different agencies, I think a lot of people won't return to public transit until they feel safe. I think a lot of people don't feel safe riding public transit right now, and they have the option not to ride. And I think that will stay as long as they feel like COVID-19 is a risk for them. But I think so I mean, on one extreme, there's maybe mass vaccination, COVID-19 is over, that's some ideal situation. And then I think under those kinds of conditions, public transit will eventually just return to what it was. I think there could be a bunch of in-between situations. I'm not a public health expert. I should have asked my wife about this before answering this question, but there are in-between situations where it's still a risk and different kinds of people don't return. But I meant what I said before. I think public transit ultimately is a force of equity, and I think cities can't survive without public transit. That I know there are a lot of fears around public transit, especially around the loss of funding. My hope, this is the idealist in me, is that this drives new conversations around how to fund public transit because it's an essential service for essential workers and for equity, instead of attaching it to ridership numbers. That's my ideal for what comes out of the situation.
Well, that seems like a great place to leave it. I want to thank all of our presenters. This was really fascinating. Thanks to each of you for your work and for sharing it with us, and look forward to the rest of the conference. So thank you all.
Thank you. I'll just jump in real quick with just a brief wrap up. Tomorrow we're going to be having our cross Canada tour, so you can visit coast to coast to coast. We'll probably start that around 8:30, bright and early. So while you're enjoying your coffee, you can fly around the country at breakneck speed. And so we'll see you tomorrow morning. It'll be the same link that you'll use to join the first plenary or the plenary 4 session in the morning. So we'll see you all tomorrow. Thank you very much.
Thanks all.